All right. So we're going to kind of keep moving ahead. I've got assignment 4 is posted to Canvas, due Monday. That's the day we get back. So, you know, it's not very long. I think I don't think it's particularly long. Or assignment 4. Oh, what? Sorry. Hold on. Let me get in the right class. Yeah, so it's not particularly long, but, you know, some of them can be a little, you know, can take a little doing. So if you have questions, I just am encouraging you to start early so you give yourself time to get stuck and ask for help, or if you want me to take a look at a draft or something. I'm working most of the break week, so just, you know, if you could send an email or a text or something, I should be able to get back to you fairly quickly. And then our first test is going to cover, I think, just chapters 1 and 2. So when we get back from break, we're going to be finishing this chapter, and I'll probably have that ready that Monday, and then, you know, you'll have like a week to work on it, a week and a half or something. If I have it ready sooner, I might post it during the break, and if I do that, I'll like send an announcement just to let you guys know in case you want to get an early look at it. Does anybody have any questions before we get started? Yeah.
Will there be an assignment due the same week that the exam is given?
No. So, like, you'll turn in assignment 4 on Monday, and then until the test is due, there won't be a new assignment given. Other questions?
When is the rewrite due for assignment 2?
For assignment 2. Monday. That's so that's this Monday. So that's a Monday during break week. If you have questions, you know, let me know. So just upload it to Canvas.
Okay, thanks.
Mm-hmm. All right, so we're going to talk about divisibility and then prime numbers. We're using, you know, here's a lot of terms that we are already familiar with. So A is a multiple of B if A is B times M for some integer M. And then this word, which is less common but used a lot actually in number theory, we say that B, that's if A is a multiple of B, that means that B divides A. Saying B divides A is the same thing as saying B is a factor of A or is a divisor of A. So we use the little, like, the pipe to denote, like, divides. So 9 divides 27. That's just a statement. It's a true statement because 27 is a multiple of 9. It doesn't tell you, like, what multiple of 9 it is, you know, like, that's on us. But saying 9 divides 27 just means that I can multiply 9 by some integer and get 27. 5 does not divide 12, and we would just put a little slash through the pipe like we do to negate the meaning of any symbol. So we're going to start off with the theorem, which will prove. First couple parts are actually pretty simple, and I will say even the first part seems obviously true. For all A, for every integer A.
Excuse me.
Yes.
Sorry, we don't see your screen from here.
Okay. I'll have to call Asher. I am sharing it. Like the screen here is on Zoom as well, so if it shows up here, I know I'm actually sharing it.
We see your desktop. Oh, I guess it's our desktop, I bet.
Yeah. I will. It's something on your end, but I can call Asher and he can fix it.
Matt saved us.
Oh, you got it?
Yes.
Okay. All right. I just hung up on Asher probably. Sorry. Okay.
Matt should get bonus points.
Yeah. All right, so for every integer A divides A. That seems like it should be true, and it's as easy to prove as you think it is. A is equal to A times 1. Therefore, A divides A. Done. Part B says, if A divides B and B divides C, then A divides C. Okay, so let's start with these. So the first part of the if is that A divides B. So, well, A divides B implies that B is a multiple of A. So that means B is equal to A times M for some M in Z. And B divides C. So B divides C implies that C is equal to B times N for some N in Z. Now let's put these together. We want to show that A divides C. So I want to show that I can multiply A by something to get C. So we know that C is equal to B times N, right? We got that from our assumptions. But we also know that B is A times M. So just sort of using the associative property, I could say that's A times M times N. So A divides C. Okay, part C. Takes a little bit more doing, but it's not terrible. If B divides A and B divides C, so B as an integer divides two other integers, A and C. B divides A and B divides C if and only if B divides MA plus NC for all integers M and N. So what that means is this expression right here, like MA plus NC, we call that a linear combination of A and C. So B divides A and C individually if and only if it divides every linear combination of A and C. So let's go in one direction. Let's suppose that B divides A and B divides C. So that means that A is equal to B times P, and C is equal to B times Q for some P and Q in the integers. Now let's let M and N be any integers. So we know that that there exists some integers P and Q, so that A is B times P and C is B times Q. There's some particular integers, we just don't know what they are. Now in this part, we're letting M be anything. Like M and N could range through any integers we might choose for them to be. And let's look at the linear combination, M times A plus N times C. And we're going to do just a little substitution. We know that A is B times P and C is B times Q. So we're going to substitute those in. So M times BP plus N times BQ. We're trying to show that B divides this linear combination, and we're just about there. Because we could factor out a B. So let's do it. So the linear combination MA plus NC is B times that integer, NP plus NQ. That means that B divides MA plus NC as desired. So that was one direction of part C. The other direction of part C is actually easier because I'm going to go back up and just read what it says again. B divides A and B divides C if and only if B divides MA plus NC for all integers M and N. So what we're going to do is suppose that B divides MA plus NC for all integers M and N, no matter which ones we pick. So So for any integer, like no matter which ones we pick for M and N, we know for a fact B is going to divide that linear combination. We're free to pick any values of M and N that we choose. So let's be clever about it. So if M is equal to 1 and N is equal to 0, if M is 1 and N is 0, then that gets us B divides A. Similarly, if M is 0 and N is 1, then B divides C, as desired. How's that? Okay. Couple theorems here. If A divides B, then A is less than or equal to B. That kind of makes sense. If A divides B and B divides A, the only way that happens is if A is B or A is negative B, which also I think kind of makes sense if they divide each other. The next theorem, the division algorithm. So basically, the division algorithm is just an existence algorithm. It just says we can do division. If we have a couple of integers, we can divide them and get a quotient and remainder. That's all it says. And the way that we write that is by saying that suppose our integers are A and B, then I can write A as B times Q plus R. In that equation, Q is the quotient and R is the remainder. For example, like if I did 29, say 29 divided by 4, right? If 4 goes into 29 7 times with 2 left over, in fact, if I just do the long division, we get a remainder of 2. So the way that we would write this out using the notation of the division algorithm is by saying that 29 is 4 times 7, there's our Q, plus 2. And the division algorithm basically says there's lots of ways I could write an equation like this, like a bunch of, take a few 4s and then add some more. I could say it's 4 times 3, that gets us to 12, plus 17, I guess, would be the remainder there. But what the division algorithm says is that there's a unique way to write this so that that remainder is between 0 and B, or in this case, so that the remainder is between 0 and 4. So that quotient and remainder is unique.
The remainder is 1, not 2.
Oh, Are you telling me that 29 minus 28 is 1? You guys. Yeah, I'm pretty sure that's 1. Okay, so definition, greatest common divisor, it is what you think it is. It is a common divisor. So if I have 2 integers, a common divisor is one that divides both of them. And then the greatest common divisor is just the biggest one of all of the common divisors it might have. And another way of saying that is that any other common divisor that A and B might have will also divide the greatest common divisor. Not that just the common divisor is the biggest one, but it will be divisible by all the other common divisors they might have. Fun facts about the greatest common divisor. The greatest common divisor of two integers is unique. The greatest common divisor of two integers exists. If, which, you know, yay. Sometimes that greatest common divisor is 1, right? Like think 7 and 12 or something, right? You think, oh, they have nothing in common. Well, everything always has 1 in common. So sometimes the greatest common divisor is 1. But regardless of what it is, whatever the greatest common divisor it is, you can actually write the greatest common divisor as a linear combination of those two integers, which is actually super useful fact. It is the least positive integer that you can write as a linear combination of those two. Is that fun fact?
Yeah. Can you show an example?
Yeah. So give me a second because I'm going to have to find... I'm going to show you... I think, you know what? We have time. Are you ready for something fun?
I'm ready.
Okay. So let's say I want this to not be a long, awful example, but a reasonable length, and sometimes it's hard to tell ahead of time what it's going to be. So let's say I'm going to find the greatest common divisor of 120 and 50, no. The greatest common divisor are 150 and 120. I hope this is gonna not be long and awful. So we can find it by using the division algorithm over and over again. This is what I hope is a short process. So 120 goes into 150 once plus 30, right? Oh, this will be probably actually really nice. Okay, then what we do is, this is called the Euclidean algorithm, by the way, which is, you don't necessarily have to know it for this class, but this is like extra at no extra charge. It's super fun. So then I take the 120 and the 30, and I do the division algorithm again on those on the next line. So I bring down the 120 here, and I say, oh, it's 30 times something plus a remainder. And in fact, it goes in 4 times with a remainder of 0. This is perfect. Okay. So the Euclidean algorithm terminates once you get to 0. Sometimes it takes many rows, and I was afraid that it would be one of those examples. But so this is just like a couple lines long, and once you get to 0, the greatest common divisor is the one above it, so it's 30. So the greatest common divisor of 150 and 120 is 30. And using this line, I can say that 30 is equal to 150 times 1 plus 120 times -1, and there's a linear combination. And 30 is the smallest positive integer that you can write as a linear combination of 150 and 120. Does that...
Okay, so
yeah.
in the first one that you have circled in red,
Yeah.
is 120 just happenstance, or is that the second number that you're trying to find the divisor of?
I started with these two, that I was looking for the greatest common divisor of 150 and 120. So then I used the division algorithm to say, okay, 150, 120 goes into 150 once with a remainder of 30. This is what the division algorithm tells us we can do.
Okay.
And then with the Euclidean algorithm, you just do it again, but with the 120 and the 30, and you bring those down.
Gotcha. Oh, okay, I see now.
Yeah. So sometimes you go through these and it might be like 4, 5, 6, 10 rows, and you could still trace it back up. It's a lot of like substituting back in. The process is long and it can be easy to make sign errors, so sometimes it's frustrating, but I feel like it's also, therapeutic. But basically it's tracing it back up until you can get to write the greatest common divisor as a linear combination. Okay. All right, part C. If A is BQ plus C, then the greatest common divisor. Oh yeah, okay. So if I've got this division algorithm, if I've used this division algorithm, and in fact, it doesn't necessarily have to be the division algorithm because they're not telling us that C has to be strictly less than B or something. But the greatest common divisor of A and B is equal to the greatest common divisor of B and C. And in fact, that's how the Euclidean algorithm works, where we say, oh, now let's bring these two down, and now let's bring these two down. And you keep boiling it down to smaller and smaller numbers. And that's how you find the greatest common divisor. That's how the Euclidean algorithm works. You can also find greatest, when we first learn about greatest common divisor in elementary school or something, we do it by just saying, let's factor the numbers and grab the factors, right? Which is great if you can factor the numbers. But the Euclidean algorithm is a super efficient way when you're working with huge numbers and that are really unwieldy. Factoring is a hard problem for computers even. In fact, it's a hard problem, and that's what makes encryption strong, is because factoring is hard. The Euclidean algorithm is a way that you can at least find, starting from given integers that, in practice might be 100 digits long or something, or just really big. It's an efficient algorithm to find a greatest common divisor that doesn't require you to know how to factor either of the numbers. It's really pretty sweet. And then the last one says that if the greatest common divisor of A and B is 1 and A divides BC, then A divides C. So let's parse that out. So first of all, what this says, if the greatest common divisor of A and B is 1, that just means if they don't have anything in common. Right? Everything has 1 in common. So we would say A and B are relatively prime or co-prime. That doesn't mean that A and B are prime themselves, but if they share no divisors other than 1, we call them relatively prime. So they got nothing in common. So A and B have no factors in common. If A and B have no factors in common, yet A divides the product B times C, the only way that happens is if A divides C. Because it has no factors in common at all with B. So all of A's factors have to belong to C if A is going to divide the product. That's what that last part says. Now, if two integers are relatively prime, right, if they have nothing in common other than 1, then there exists integers such that A times U plus B times V is equal to 1. This is just a restatement of this part here, and where we wrote, when we looked at 150 and 120, and we said, we could write their greatest common divisor, which is 30, as a linear combination. So of special importance is if you have numbers that are relatively prime, that means you can write 1 as a linear combination of those two numbers, and in number theory, that's actually kind of an interesting and useful result. Least common multiple, again, I think we know least common multiple. Least common multiple is, first of all, a common multiple, and it's the smallest one that they have in common. So if M is the least common multiple, then A divides M and B divides M. It's a common multiple. But also, if A and B also divided some other integer, if there was some other common multiple, then M, the least common multiple, will divide it. And then we're going to finish up this section with a result that we'll prove.
It's hard to think about the least common multiple as not being the least common multiple. Because it's the least multiple, right?
It's the least common multiple.
Okay, I don't understand.
So the least common multiple is a common multiple.
Right.
And it's the least of them all.
It's just, so it's not the smallest.
It is. It's the smallest multiple.
The way I was parsing it was, it's the least common, meaning it appears less.
Okay. Yeah, no.
So it is the smallest multiple
Yes.
that is common amongst.
Yes. Okay. Yep, that's what we mean. It's really, yeah, it's rare. No, two integers always have a least common multiple. All right, so let's think about linear combinations. So the equation ax plus by equals c, where a, b, and c are integers. So we imagine a, b, and c are some maybe particular integers, right? Like they're fixed. And it has an integral solution, and by integral solution we mean integer solution, if and only if c is divisible by the greatest common divisor of a and b. So if you imagine that a, b, and c in this equation are fixed integers, an integer or integral solution would be values of x and y that will satisfy the equation. And what this theorem says is that that equation will have integer solutions for x and y if and only if c over here is divisible by the greatest common divisor. Remember that we already said on the previous page that the greatest common divisor is the least, it's the smallest integer that can be written as a linear combination of a and b. So this is sort of a extension of that. When this is the case, a solution is given by those two values where u and v comprise any solution of this. So here, I'm just going to scroll back. When we, in part B, right, this highlighted part, when we just said, oh, the greatest common divisor can be written in the form, can be written as a linear combination. Not necessarily in a unique way. There might be more than one way you can write the greatest common divisor as a linear combination. That's why this says where u and v comprise any solution of this. Right? They're just saying that the way we can write the greatest common divisor as a linear combination may not be unique, but we know it exists from the theorem on the last page. So we're going to start with this direction. And that means that that means that we're going to suppose that C is divisible by the greatest common divisor of A and B. And then we're going to show that that equation has an integral solution. So let's let D be the greatest common divisor of A and B. And suppose that D divides C. So that C is D times M for some integer M. So this means that M is C over D. Now, if we go back, I'm going to scroll back to this page in just a second, but looking at this result, using part B, we're going to use this. We know that there exists integers u and v so that we can write D as a linear combination of A and B, and we're going to use that. So that u times A plus v times b is equal to D, the greatest common divisor. So now we have an equation. That's pretty nice. Let's multiply both sides by M. So we get AUM plus BVM equals DM. What's D times M equal to?
C, right?
Yep. And we know it's C from up here, right? Because we suppose that D divides C, so that C was D times some integer M. And on the left side here, I'm just going to rewrite this by kind of emphasizing the grouping. We basically have the result that we want. M is an integer, U and V are integers, so UM is an integer and VM is an integer. There's our integer solution. So here, X is equal to UM and Y is equal to VM. And then the last bit is just substituting. So now substitute M equal to C over D to get X is equal to U C over D and Y is equal to V C over D. And that just gets us the other part of the result that we're looking for. I'm going to scroll up real quick. That's this part where it said a solution is this part. Remember, we called the greatest common divisor equal to D, so that we've just sort of established the result that we wanted in that direction. All right, I think that was the harder direction. I think I might have left more space to do the other direction. Are we ready to scroll? Does anybody need me to stay put for a minute? Okay. All right. So for the other direction, we're going to suppose that that equation, ax plus by equals c, has an integral solution. So, in other words, let's assume there are integers, x and y, such that ax plus by equals c. And what are we going to show? I'm going to scroll back up. I'm scrolling back down in just a second, but we're assuming that this equation has an integral solution. So now we're going to show that C is divisible by the greatest common divisor. We want to show that D divides C. We know that D divides A and D divides B because it is the greatest common divisor. So we know D divides A and D divides B. That means that A is equal to D times M and B is equal to D times N for some integers M and N. Now, we have an equation that we get to use, right? We know that ax plus by equals c is an equation of integers. Let's start with that equation. And I'm just going to make some substitutions. I'm making a substitution for a here and for b here. So we have dm times x plus dn times y is equal to c. We're trying to show that d divides c. What can we do on the left side there?
Factor out of d.
Yeah. Factor out of d, we have mx plus ny. What does this mean?
Is it that like mx plus ny is an integer?
We do know that mx plus ny is an integer. Yep.
Because we know that d multiplied by some integer, if I can speak, is equal to c, we can say that d divides c.
Yeah, that's exactly what we can say. Okay. Fun? Questions? Okay. Let's talk about primes. So a prime number, we've already talked about this before, it came up in one of the problems that we were doing, but prime number is a natural number greater than 1 whose positive divisors are 1 in itself. And a composite number is a natural number greater than 1 that's not prime. So if you could factor it down, it's composite. If you can't, it's prime. If it's 1, it's special and like in its own category. There are infinitely many prime numbers, and we're going to prove it. Let's suppose, for contradiction, that there are finitely many primes. You know what you can do with a finite set of things? Anybody know?
Count them.
Sorta, yeah. Close. We can list them. We can write them down in a list. So we're going to write down all of these finitely many primes. Are you ready? P1, P2, P3, all the way up to PK. So there are K many primes. That's the finite number of primes that there are. We're going to be constructive in this proof. Here's what we're going to do. I'm going to sort of tell you the approach. Obviously, we're using contradiction as the approach, but here's the construction that we're going to make. Is we're going to use these primes that we have, and we're going to make a new number from these primes, and we're going to be able to say that that new number is not divisible by any of these primes. And if it's not divisible by any of these primes, that means it's either divisible by a prime not on our list, or it's prime itself, right? Either of those things causes us to conclude that we couldn't list all the primes, right? And that's the contradiction that's going to force us to conclude that there are infinitely many. So here's how we make this number. It's really pretty clever, I think. I'm going to call it big N. I'm going to take the product of all of our primes, P1 times P2 times P3 times. So I've multiplied all those primes. If I stop there, that number is divisible by all of those primes, right? But I'm not going to stop there. I'm going to add 1. So we'll note that n is definitely bigger than any of those primes. And so that means it must be composite. If it's composite, it has a prime factor. So I'll call that factor P sub r. So if PR divides n, that means that PR divides this product plus 1. If PR is a prime factor of n, then by our own supposition, PR has to be one of these primes, right? We said we listed them all. So it's got to be one of them. That means that we know for a fact PR has to divide the product from P1 up to PK. So look, PR divides the product plus 1, and PR divides the product itself. So the only way that that's true, the only way that PR can divide the product itself and the product plus 1 is if PR divides 1. It's got to divide that other term if it divides the whole sum. And that's a contradiction. So what this forces us to conclude that either n is prime or has a prime factor that's not on our list. And that's another contradiction. Must be we weren't able to list all the primes. Right? Something wrong with that assumption. So there must be infinitely many primes. So there are infinitely many.
Question about proof by contradiction. So if you if you assume two things
Mm-hmm.
and you're going for a proof by contradiction, would you have to prove that the statement that you're not trying to prove is contradictory to be true in order to say that since assumption 2 is correct, then assumption 1 must not be?
I'm not sure I understand. Like,
So like, let's say we have something to prove.
Uh-huh.
We assume things.
yeah.
So if we have two assumptions.
Yep. So assumption A and assumption B.
If we're trying to prove by contradiction, do we have to prove that if we want to prove, let's say, that assumption A is faulty, would we have to prove that assumption B is accurate?
No, I don't think so. Not unless.
Because you see what I mean? You basically.
I mean, so here's what if you assume two things, it's like, if your assumption is compound in that way, either the contradiction you reach in such a way that you can tell that there's something wrong with just one of your assumptions, right? Like the contradiction you reach might be specific and say, oh, must be assumption A is wrong. That would be, I suppose, if you didn't rely on assumption B, or if you did rely on this. Otherwise, it might just be like, but these both can't be true. You know what I'm saying? Like, as a group, you'd have to reject the group, but I don't know if you could say specifically assumption A or assumption B. Maybe it's the two of them acting together. But you can just say both of these assumptions can't be true at the same time. It would depend. I guess I'd have to look at like a particular scenario to see if, depending on what you had to use as you were writing the proof, if you could actually pinpoint it to assumption A versus assumption B.
What I'm kind of thinking is that if you are doing a proof by contradiction, then you can only assume one thing, which you then try to contradict.
Yeah, well, that's usually what we try to do. Like, if I'm using contradiction, I want to, like, here we're trying to prove that there are infinitely many primes. So usually you just assume the negation. Like, assume that's not true, right?
Right.
And that's a really simple assumption. I guess maybe this is a simple example. But usually you just start out by saying, suppose this isn't the case. Like, really general, just the negation. Try not to get too specific. But just as much as you need to assume to just have it be the negation of what you're trying to show.
Okay.
Other questions? Okay. If the positive integer n is composite, then n has a prime factor p such that p squared is less than or equal to n. I like this theorem. It's, as you can see, I didn't leave a lot of room. It's pretty easy to prove. But this is a useful result because if I'm looking to factor a number, if I'm not sure if a number's prime, right, and I just am looking for factors, this tells me I don't have to look that far. If I'm looking for prime factors, first of all, if I'm looking for factors, I have to look for prime factors, right? Like if something's not divisible by 2, it's not going to be divisible by 4 or 6, right? But then I don't have to check all the primes up to n. What this theorem tells me, the result is that if I'm looking for factors of n, first I'm going to start, I'll use my calculator, take the square root of n. It'll probably give me some decimal result or something. And then I only have to check primes up to that number. And then if I haven't found any prime factors by the time I get to the prime that's closest to the square root of n, there aren't any. Because this says that if n is composite, like if I can factor it, it'll have a prime factor that such that p squared is less than or equal to n. So let's let p be the smallest prime factor of n. And actually, before I go any further, I want to just state further. When I said you take the square root to like give yourself a limit, that doesn't mean that there aren't bigger factors of n. Like, that doesn't mean that there aren't factors of n that are bigger than the square root of n. but it just means that any factors that you found bigger than that number would have their partner factor on the other side of the square root of n. Does that help? Okay. All right. Just wanted to be clear. So let's let P be the smallest prime factor of n, and let's suppose that we can factor n as the product r times s. It doesn't have to, not necessarily prime factorization, but we could write it as the product r times s. So we chose P to be the smallest prime factor. That means that P is going to be less than or equal to R, and P is less than or equal to S for sure. If P is less than or equal to R and less than or equal to S, then P times P, or P squared, is less than or equal to R times S, which is equal to N. Right, that gets us P squared less than or equal to N. Questions? Okay. Is there a question?
Yeah, I was wondering if you could just run through it one more time.
Yeah.
I didn't really follow.
Yeah, so we're letting n be the smallest prime factor, or sorry, we're letting p be the smallest prime factor of n, right? So n is composite, and I could find its prime factorization. P is the smallest prime that divides n. And part of our assumption here is that n is composite, so I could factor it. And here I'm just giving any old factorization. So like n is r times s. R and s don't have to be prime factors. This isn't a complete factorization, but I'm just saying I can write n as the product r times s. But because p is the smallest prime factor, for sure, if p is the smallest prime factor, it can't be bigger than r or s, right? It has to be less than or equal to r, less than or equal to s, because it's less than or equal to any of the divisors of n. So then p squared, and in fact I'm going to just extend this. P times p is going to be less than or equal to r times s. Like I'm taking something less than or equal to r and multiplying it by something less than or equal to s. So p times p is less than or equal to r times s. Of course, p times p is p squared. And what we have here, when we look at this string of equals and less than or equal to, I've got p squared, I'm maintaining equality, this is less than or equal to maintaining equality n. And putting those together gives me that p squared is less than or equal to n. Does that help?
Yeah, thank you.
Okay. Other questions?
The next theorem says Euclid's lemma.
Mm-hmm.
What is it a lemma to?
A lemma is just a smaller result that's used to prove other results. So,
It's not necessarily
for
lemma.
dilemma.
what's that?
Not short for dilemma.
Not short for dilemma. No, a lemma is just a is a result like theorem, lemma, proposition. They all have essentially the same meaning, but some they tend to use theorem not exclusively, but more often for more weighty results. And lemma is used almost exclusively for something short, like a short result that might be used to prove something more general or bigger, or maybe it's used so often. Like Euclid's lemma is actually pretty useful and gets cited a bunch of times. So, and it doesn't, as you can see, doesn't take that much space to prove. Euclid's lemma says that, so P is a prime, and we have a prime that divides a product, A times B. A and B need not be prime, right? It's whatever, it just divides some product, A times B. That in order, the only way that this prime number P is going to divide a product A times B is if P divides A or P divides B. And that kind of makes sense. Like, you know, if, like, I'm going to give you a couple of examples just to illustrate that it's important that P is prime here. So, you know, 4 divides the product 6 times 14, okay? But 4 does not divide 6 and 4 does not divide 14. This is why it's important that P be a prime in Euclid's lemma. I could think of 4 as just a pair of 2's, right? So in a way I could kind of devise a product where each of these 2 factors has a single 2, so that altogether 4 does divide the product, 6 times 14, because there are couple factors of 2. I could kind of partition out the factors of 4 between the factors, you know, of those 2 numbers. But you can't partition out the factors if it's prime. If it's prime, there's only one factor to dole out, right? And so that single factor, like if I have 3 divides, you can't come up with a product that it will divide without 3 having to divide one of those, because there's only one factor. I can't split the factors of 3 and dole them out in between the 2 numbers. So like, you know, 6 times 14, like 3 divides 6, that's true because 3 divides 6. So if you have a prime that divides a product, the only way that happens is if that prime number divides one of the factors in the first place. And we're going to prove it. So let's suppose that P divides AB. If P divides A, we're done. Right? Like, we're trying to show that P divides A or P divides B, that one of those has to be the case. So if it is the case that P divides A, we're all done. So let's suppose that P does not divide A. What are we going to show? Yeah. We will show that P divides B. Okay, because P does not divide A, and P is a prime, right? P is a prime that does not divide A. That means that A and P are relatively prime. That means that the greatest common divisor of A and P has to be 1. And now we're going to use that result that we showed, that we talked a lot about actually in the last section. We can find integers and write 1 as a linear combination of A and P. So we can find integers U and V such that A times U plus P times V is equal to 1. Now we have an equation, and I got to tell you that's a pretty good spot to be in. We are trying to show that P divides B, and what is conspicuously absent from this equation? So here's our goal.
B is absent.
Yeah, B is absent. We're trying to show P divides B. We have this nice equation. B is nowhere to be found. So let's put it in there. Let's multiply by B. So we have AUB plus PVB is equal to B. Now we know for sure that P divides PVB, right? It has to. There it is. There's that factor of P. If only we could show that P divides AUB. Because if it did, then if you divide this term and this term, you have to divide the sum. How do we know that P has to divide AUB?
Because according to PVB equals B, P divides B.
According to what?
So, according to the second half of that, the PVB equals B. Well, B is a common factor there, so.
Well, yeah, B divides it.
I knew, but I don't.
Okay. All right. I mean, B certainly is a common factor, but we want P to be a common factor. We're trying, like, we know P divides this term, right? Because we could see the factor of P right there. How do we know that P divides that term? Because once we have that, like, if P divides both terms, then it has to divide the sum, right? How do I know it divides AUB? Because it does.
Just thinking out loud here, P doesn't divide A, so you would have to divide UB if that were true, right?
P doesn't divide A, but what does it divide? What did we start out with?
AB.
Yeah, P divides AB. That's the very first line, right, of our proof. Suppose that P divides AB. Well, if it divides AB, it certainly divides AB times U, right? So that's how I know it divides AUB. And so P divides the sum. AUB plus PVB, which means that P divides B. Okay. Questions? Okay. All right, so here's a corollary. A corollary is just a result that generally follows from a broader result, like kind of expanding on a result. So if P is prime, and it divides a product, now not just the product of two numbers, but a product of these n numbers, q1, q2, up to qn, then P has to divide one of the q's, right? So we're just taking it from the case where we looked at only two factors to if P divides the product of a bunch of things. The only way that happens is if P divides one of the things. We're going to prove this by induction on n. If n is equal to 1, then the statement is clearly true. Because the statement is if P divides Q1, then P divides Q1. And that's obviously true. So now for our induction step, let's suppose it's true for some n equals k. And further suppose that P divides the product Q1, Q2, QK times QK plus 1. What I'm going to do is just group these factors in a way that's helpful to me, right, and to our goal. I've written it as P divides the product of these K plus 1 factors. But I'm just going to group them in a helpful way. And here's how I'm going to do it. I'm going to segregate out the factors Q1 to QK, put those in a group, and then say times Q sub K plus 1. Now what I'm doing is I'm taking what was written as a product of a bunch of things, and I'm looking at it as a product of two things. I've got two things. I've got this factor, this Q1 through QK, that's some integer. P divides this block times Q sub K plus 1. So then by Euclid's lemma, it either P divides the product Q1, Q2 through QK, or QK, or P divides Q sub K plus 1. If it's the case, so one of these two things is the case, right? Either P divides the Q1 through QK or P divides Q sub K plus 1. If P divides Q sub K plus 1, we're done.
So we assume that it doesn't.
We don't need to assume that it doesn't, because actually the result is going to follow by induction. One of these has to be true. If it's this one that's true, we're all set. If it's this one that's true, right, then we just use our induction hypothesis. Because we said, suppose it's true for some n equals k. If it's true for some n equals k, then if P divides this product of k factors, it's got to divide one of them. Then P divides Q sub I for some I by our induction hypothesis. And now the result follows by induction. Okay, we're almost done. We've got another sort of quick result that we're not going to prove, but we'll We'll just talk about its importance. We'll do a little factoring, and then we'll be done for the week. The fundamental theorem of arithmetic says that any natural number greater than 1 is either prime or it can be written as the product of primes. Furthermore, that product is unique, up to like rearranging the order in which you write the numbers. So like 2 times 2 times 3 is the same as 2 times 3 times 2, right? So we stipulate that you could rearrange the order. But other than that, like the selection of primes, the way you could factor a number is unique down to primes. So real quick, if we wanted to factor this number, as it turns out, I mean, we could go through the whole factor tree, but if you factor it all the way down, you have a 2, you got a 3, you got a couple 7s, you got an 11, you got a couple 13s. That is like its kind of molecular structure, if you will, of that number. The collection of primes, like what primes are there and how many of each, defines this as a number, and there's no other number that is defined by those primes in that selection. When we write this factorization, we say that this is the prime factorization, that we're writing it in like a canonical form. Usually you just list the primes, and instead of saying 7 times 7, we'll write 7 squared. We use the exponents to do that. And then a couple results. Suppose that A has a prime factorization like this, like P1 to the alpha 1, P2 to the alpha 2, like we have written its prime factorization. If I know that B divides A, that means that B is some product of the same primes, just possibly to different powers. In fact, we know that all of the powers on the primes for B have to be less than or equal to the powers on the primes here. Like you can't have an extra factor of 2 that wasn't present in A if B divides A. And it's also possible that one of these betas could be 0, right? Like you don't have to have all the primes, right? But it like if 2 divides, if A has a factor of 2 cubed and B doesn't have any factors of 2, in this theorem, they would say, oh, we would consider that to be like 2 to the 0 or something. So this just says if I know the prime factorization of A, then any number that divides A, I'm going to find just by selecting some of those primes. That's how I get any divisors of A. And then the last result just says if I got a couple numbers, A and B, if I find the greatest common divisor and the least common multiple, and I multiply them together, you will always get the product A times B. And that's a fun fact. And look, a minute to spare. Done early, before a break. What are you going to do with all this extra time? Okay, please take a look at assignment 4 that's due the Monday you get back. I'm working pretty much most days during the break, so email or text if you have questions or are stuck or want me to take a look at a draft.